Okay, let's have a look here at this this other system here. This is this looks like terrifying, but it's not actually terrifying. There's just a whole bunch of different things happening here. So let's break it down to see what's going on. Okay, first of all, here is our balanced equation. Nitrogen monoxide plus oxygen goes to nitrogen dioxide. Delta H is less than 0. So this means that the forward reaction is exothermic. Please excuse the terrible writing. Okay, but the forward reaction is exothermic if delta H is less than 0. So for any equilibrium system, we should also have a look at not just the delta H to figure out if the forward reaction is exothermic. These are all gases. We need to look at the moles of gas. So the first thing we do with any equilibrium reaction and the graph is figure out what we actually already know. It's better to go into the graph looking at what you do know. So we've got 2 plus 1 is 3 moles over here and 2 moles on the right. So the forward reaction in this system will decrease the pressure. Okay. So then let's go have a look at the graphs here. The first thing to see is this is a concentration graph and this is a rate of reaction graph. So these two look very, very similar. The way to, if you had no labels on the axis, the way to tell them apart is that on the rate graph, at equilibrium, everywhere where the system is in equilibrium, the two lines are on top of each other because the equilibrium definition says to you, equilibrium occurs in a closed system when the rate of the forward reaction equals the rate of the backward reaction. Okay, so in any system, the forward reaction always starts at a high rate and the reverse reaction at a low rate, because whenever we start, we're full of reactants and have 0 products. So right at the beginning of this, there's a very, very high concentration of reactants, and they very rapidly react to form the nitrogen dioxide and come to equilibrium. So here's my container when I started my container. And here, eventually when it goes flat, is the concentration of my reactants. You can see here that my concentration of oxygen has actually gone below my concentration of nitrogen dioxide. Wherever the line is, it actually doesn't really matter so long as you're following the process more than the actual physical level, unless you have to do a calculation. So you just know that the concentrations are going to decrease because they are reactants, okay? And the rate of reaction of the forward reaction is initially very, very high, because if you imagine a number here like 0, 1, 2, 3, 4, 5, the rate of reaction is here 5 and here 0. So the rate of the forward reaction is initially very, very high, but then as the concentration of my reactants drops, the rate of the forward reaction has to decrease. So the rate of the forward reaction just keeps decreasing. And then obviously as you make the products in a reversible reaction, the rate of the reverse reaction will increase, because as you're doing the reaction, you are increasing the product, you're increasing the concentration of the reactants. So here we go, we've started with the things in the container. The nitrogen dioxide and oxygen is being used up until we reach equilibrium. And so on the rate of reaction graph, the two lines are meeting. So now we have an equilibrium system, and Le Chatelier says, okay, what is going to happen in this equilibrium system? So the first thing we have to do is we have to say what happens if you increase the pressure. So in this block 1 is an increase in pressure. Remember, an increase in pressure will always increase reaction rate, because an increase in pressure is just like having an increase in concentration. And remember, the rules of reaction rate says if you increase concentration, you increase reaction rate. So we are going to increase the reaction rate of every single reaction in this vessel. So the forward reaction and the backward reaction is going to increase. However, if we want to have a look at this, we need to decide which reaction is going to be favored by an increase in pressure. So we have to look at the number of moles in the container. So with an increase in pressure, according to Le Chatelier, we want to decrease the pressure. So this system, if we have a look at this system, the forward reaction, can you see the forward reaction will decrease the pressure? okay, because we are going from 3 moles to 2 moles. So the forward reaction decreases pressure. So here, look at the concentrations here. Increasing pressure is exactly like increasing concentration. So the moment here at T equals 1, we squashed the system to increase the pressure. All of these, can you see? All of these shot straight up. But now as the system tries to rebalance itself, what will happen? The forward reaction is favored because the forward reaction decreases pressure. What does the forward reaction produce? The forward reaction produces nitrogen dioxide. So my nitrogen dioxide is going to be increased, okay? So here it went up because of the pressure, but with the new system we will end up, can you see here's the equilibrium, the previous equilibrium. I'm looking at the wrong graph, colored in the wrong thing here. Okay, look here, here's my nitrogen dioxide, which is my product. Here's my nitrogen dioxide, it's climbing, 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 and then as we increase the pressure, concentration effect, zoom, it zoomed up, and now it carries on climbing over here because an increase in pressure favors the forward reaction. The forward reaction produces nitrogen dioxide, so nitrogen dioxide has gone up. At the same time, to make nitrogen dioxide, the nitrogen monoxide has to go down and the oxygen has to go down. And then we have reached a new equilibrium state here, but you can see the new equilibrium state has a higher concentration of nitrogen dioxide than the previous state. The previous state was there, now it's here. Then if you look at the reaction graph, both reactions were favored by an increase in pressure, but the forward reaction rate kept increasing with the increase in pressure, whereas, the backward reaction, I'm talking nonsense here. Bear with me. This is very tricky to talk about without getting tongue-tied. Let's go back here. Increase in pressure favors the reaction that decreases pressure. So the first thing we see on the graph here is the sudden straight rise upwards with both of the reaction rates, because an increase in pressure is like increasing concentration. Increasing concentration increases reaction rate. But if we look at these two graphs, the forward reaction has gone up more than the backward reaction. Why is this? The forward reaction was favored because the forward reaction decreases pressure. So as you increase the pressure, both reactions are favored, but the forward reaction is favored more, so its rate is higher. And then here is the new equilibrium position over here, and the increase in pressure means the overall reaction rate is higher. If you were to read rate of reaction off the side here, the overall reaction rate is higher because it is got a faster reaction because of the increase in pressure. So then the next one here is a decrease in pressure. So in this zone 2 here, we have a decrease in pressure. Now the moment you decrease pressure, you decrease the concentration of everything. So you can see everything here has gone down with a decrease in pressure. A decrease in pressure is like a decrease in concentration. It slows down the reaction rate. So both of these reaction rate graphs are going to immediately drop because the reaction rate is decreased. But now we need to figure out which one of these is going to drop more. So if we decrease in pressure, the backward reaction results in an increase in pressure. So according to Le Chatelier, if we decrease the pressure, we will favor the backward reaction because the backward reaction is what actually increases the pressure. So if you have a look here, if the backward reaction is favored, it's the solid line, it is favored, so its rate is dropping less. The forward reaction, look, it was at this level here, this rate of reaction, say this was 5 and this is 2, and then the backward reaction will be at 3. You can see by favoring the backward reaction, it has dropped less. The forward reaction dropped more. It has a much, much slower rate with a decrease in pressure. Now the next one says to you, what happens if you add oxygen. So in zone 3 over here, it's when we add oxygen. Which side of the equation is oxygen? Oxygen is on the left. It is a reactant. So what is the system going to do? If you add a reactant, the system wants to get rid of it. It gets rid of it by favoring the forward reaction. So we're going to produce more nitrogen dioxide. So if you look at the graph here, only oxygen is added. So in the concentrations, this concentration and this concentration have stayed the same, but the oxygen concentration has skyrocketed. So the oxygen concentration has increased, and adding a reactant favors the forward reaction. So you can see here, when we added it, the forward reaction immediately went upwards as well. So once we've got the forward reaction favored, this is the new level of oxygen after we added it. It starts being used up and getting less because the forward reaction uses this up, and then immediately our concentration of nitrogen dioxide starts increasing because that's what the forward reaction produces, until we get to this equilibrium. So here you can see on the rate graph, the forward reaction is favored. It goes up because the forward reaction gets rid of the extra oxygen. And then we have a new equilibrium system that is higher than this equilibrium system because we had additional reactants in there. So the more reactants you have, the higher the reaction rate, and that's why this equilibrium position is higher than that one. Then let's have a look here. What happens if you remove nitrogen monoxide? Now, which side of the reaction is nitrogen monoxide? Here is the nitrogen monoxide. It is a reactant. So if you remove the reactant, the system wants to increase its concentration. Okay, so if we've taken this out, the system says, let me put it back in here. So the system is going to favor the backward reaction here if you remove the nitrogen monoxide. So here, if it's the nitrogen, can you see the solid line is the nitrogen monoxide graph? So the nitrogen monoxide zooms downwards. My other two levels stay the same. So this is how we can tell it's the nitrogen monoxide that's been removed. The moment we remove a reactant, the reactions will all slow down. So we're going to end up with the reaction rate at a lower level over here. But which reaction is favored by this removal? The backward reaction. So the backward reaction's rate has decreased less. The forward reaction here, which is the dotted line, its reaction rate has decreased a lot. It went right down because the forward reaction was not favored. So this level, this rate that you're reading off the graph here is now very low. And the overall rate at equilibrium is lower than the previous rate because we have got less reactants. So this is what is happening here. Removing the reactant favors the backward reaction, and the backward reaction being favored increases the levels overall of both the two reactants, nitrogen monoxide and the oxygen here. The dotted line and the solid line, not the dashed line. Because remember, the dashed line is the nitrogen dioxide that has decreased. Then we come to here, an increase in temperature. If you increase the temperature, the system wants to decrease the temperature. So this forward reaction is exothermic. The backward reaction is going to be favored by an increase in temperature because the backward reaction will decrease the temperature. Remember, we know this reaction is exothermic because delta H is less than 0. Secondly, when you increase the temperature, you have to bear in mind that in actual fact, all of the reaction rates will rise because increasing temperature gives the particles more kinetic energy. So the more kinetic energy you have, the greater the rate of reaction. So we will increase the rate of reaction for both the forward and the backward reaction, but we will increase the rate of the backward reaction more. So here's the backward reaction. It is the solid line. It is increased more than the forward reaction, but the increase in temperature gives the particles more kinetic energy, so we have an increase in reaction rate. But because the reaction is exothermic, the backward reaction is favored, so the backward reaction goes up more than the forward reaction. And if the backward reaction is favored, we will end up with a higher concentration of reactants. So you can see here, these two are my reactants, the dotted and the solid line. They go up and form a new equilibrium at a higher level. And as they are going up, the nitrogen dioxide is going down. And then finally we're at this new equilibrium. And if we look at the last thing, it is a decrease in temperature. Decrease in temperature always decreases both forward and backward reaction rate, but it will decrease depending the one reaction depending on Le Chatelier. So if we decrease the temperature, Le Chatelier says we will favor the exothermic reaction. So here, the decrease in temperature has dropped both reaction rates. You can see them dropping. But the backward reaction, can you see it has dropped a lot, and the forward reaction has only dropped a little bit, because decrease in temperature always lowers reaction rate. So now, because this decrease in temperature has favored the forward reaction, because the forward reaction is exothermic, the forward reaction produces nitrogen dioxide. So boom, here goes my concentration of nitrogen dioxide up again. And in order to increase this concentration of nitrogen dioxide, the levels of the nitrogen monoxide and the levels of the oxygen must go down. So the two graphs are similar, but they're not the same. But you just have to say, okay, if the forward reaction is favored, my product will increase. If the backward reaction is favored, my product will decrease and my reactants will increase. And you figure out which reaction is favored by doing the opposite of whatever change was put on the system.